Hello and welcome to News About Geology. You know, every single gemstone you've ever seen holds a story, a secret history written right into its atoms. Today, we're going to become geological detectives. We're going to learn how to read those secrets and uncover the incredible journey of a gem, from deep inside the earth right into the palm of your hand.
So just take a look at this gorgeous ruby. I mean, it's brilliant, it's fiery, but it's also a total mystery. Was it forged deep within the earth over millions of years? Or was it, grown in a lab last week? And if it is natural, did it come from a legendary mine in Burma? Or maybe somewhere else entirely? These aren't just trivial questions. They define a gem's value, its story, and its entire identity.
And that leads us to the big question, right? In a world with super sophisticated treatments and amazing lab-grown alternatives, how can we be absolutely certain where a gemstone came from and whether or not it's the real deal? Well, the answer is hidden in its chemical story. All right, so here's our game plan for this explainer. First, we'll explore the secrets hidden deep inside a gem. Then, we'll open up the high-tech toolkit that chemists use to uncover them. After that, we'll learn how to read a stone's chemical fingerprint, tackle that ultimate challenge of natural versus synthetic, and finally, we'll get a peek into the incredible future of gemology.
You can think of every single gemstone as a tiny time capsule. Its unique chemical makeup is basically a historical record of the insane pressures and temperatures that formed it. These details, right down at the atomic level, tell a story that no two gems can ever share in exactly the same way.
You know, back in the day, a sharp eye and a magnifying loupe might have been enough, but not anymore. The modern gem trade is so advanced, so sophisticated, that a simple visual inspection just doesn't cut it. To solve today's gemological puzzles, we have to bring in the heavy scientific artillery.
And that brings us to the tools of the trade. Let's take a look at the incredible instruments that let us peer deep inside a stone and read its atomic recipe. This is where things get really cool.
First up, we've got something called X-ray fluorescence, or XRF for short. This method is brilliant because it's completely non-destructive. You basically bombard the gem with high-energy X-rays, and in response, the atoms inside start to emit their own unique X-rays. It's kind of like making the stone sing its own chemical song, and the spectrometer listens to that song to figure out exactly which elements are inside.
But XRF is really just the beginning. For the really tough cases, we need to bring out an even more powerful tool: laser ablation inductively coupled plasma mass spectrometry. Yeah, that's a mouthful, so we'll just call it LAICPMS. While XRF is great for the major elements, this machine has unbelievable sensitivity. It can detect even the tiniest, faintest trace elements.
And here it is, the absolute powerhouse of the modern gem lab. The way this thing works is just fascinating. A high-powered laser takes a tiny, basically invisible biopsy from the gem's surface. That microscopic sample then gets vaporized into a super-hot plasma and shot into a mass spectrometer, which then reads its complete elemental DNA.
And when I say tiny, I really mean it. The little pit left by the laser is just 55 micrometers across. To give you some perspective, that's smaller than the width of a single human hair. It's completely invisible unless you're looking under a microscope. Just incredible.
It's this kind of remarkable technology that just gets me so excited. And hey, if you're as fascinated by these incredible geological tools as I am, you can see a lot more of them on my personal YouTube channel. You can find it at youtube.com/aboutvalsgeoconsultant/videos.
Okay, so we've seen the tools. Now let's put them to work. It's time to find out how just a few atoms of a trace element can pinpoint exactly where on planet Earth a gemstone was born.
This table is a perfect example of a chemical fingerprint. Let's take parabitormalene. Stones from Brazil, they have a distinctively high copper content. The ones from Mozambique, higher gallium, and those from Nigeria are rich in strontium. These subtle differences, totally undetectable to the naked eye, act like a geological passport, stamping the gem with its precise place of origin.
All right, now for what is often the biggest, toughest challenge in all of gemology: telling the difference between a stone that grew in the Earth's crust and one that was created in a high-tech laboratory. The clues can be, well, unbelievably subtle. Let's take emeralds, for example. One of the most fascinating telltale signs is hidden right there inside the crystal structure itself: water. And what you're looking at here are graphs that show the unique spectral signature of water molecules that were literally trapped inside these emeralds as they formed.
And this is the brilliant part. According to researchers Shelementiv and Surov,
Natural emeralds always show two distinct types of water peaks. But hydrothermal synthetics, the ones grown in a water-based solution, they only show one. And flux-grown synthetics, which are made without water, show none at all. The presence and the type of water give us undeniable proof of an emerald's origin.
And this cat and mouse game extends to so many other gems. Jadeite has been synthesized, but it's not made commercially, so most synthetic jade you see online is actually a totally different material. For centuries, the famous Black Prince's ruby in the British crown jewels was thought to be a ruby. Turns out, it's actually a spinel. And with rubies and sapphires, labs can use a bunch of different methods to create them, and each one leaves its own faint, ghostly clues for gemologists to track down.
So what happens when the chemical clues get too complex? When there are just too many variables for the human eye to reliably figure out? Well, that's when we turn to the next generation of detective work, artificial intelligence.
Here's the problem. For some gems, like rubies and sapphires, the chemical signatures from different mines can overlap a whole lot. And when you plot them on a simple 2D chart like this one, it's just a messy cloud of data points. The signal you're looking for is completely buried in what we call statistical noise.
But this is where machine learning is an absolute game changer. While we can't see in more than 3 dimensions, a computer can analyze dozens. By adding other trace elements as extra dimensions, these algorithms can sift through that cloud of data. They progressively filter out the noise until, boom. As you see here, the algorithm reveals a clear, confident match. This sapphire has been pinpointed to a Sri Lankan origin. It's just amazing.
This technology is constantly getting better, constantly pushing the boundaries of what we can discover. And it leaves us with a really fascinating thought. As our tools get even more powerful, what other incredible secrets are just waiting to be read from our planet's oldest and most beautiful treasures?
From a simple visual inspection to this kind of complex, multi-dimensional data analysis, the quest to understand a gemstone's true identity is this incredible journey through science and history. If you want to continue exploring this amazing world of geology with me, please do visit my YouTube channel. Thanks for watching News About Geology.